Hi everyone, welcome back to another episode of Maths Explained for a Layperson. For this first question, we're going to be covering what's known as a proof by induction, and the question that we have to prove, or the statement we have to prove, looks something like this. So, here's our statement. We have on the left hand side, n plus 1 plus n plus 2 plus ... plus 2n equals n times 3n plus 1 on 2. And we have to show that this is true for all integers n greater than or equal to 1. This might just look like a lot of symbols, so we're going to break down exactly what this means. What this statement means for some integer n is that we sum the numbers starting at n plus 1, and then going by increments of 1, we add all those numbers going up 1 each time to the integer just right below 2n, and then add 2n. So for an example, if what this statement would mean when n is equal to 6, so we start at n plus 1, which would be 7, and then we add the next number, which is 8, and we keep going up increments of 1, all the way until we get to 2 times 6. So this would be 12. That's the left hand side when n equals 6. So we're just starting at the number 1 above, going up by 1 each time until we get to the number 2 times n. And what does the right hand side look like? That's a bit easier because it's just a single expression. This is literally just we substitute our value in. So for example 6, it's 6 times 3 times 6 plus 1 divided by 2, which is equal to 6 times 18 plus 1, which is 6 times 19 on 2, which is 3 times 19, whatever. And once you work it out, it happens that this expression, or all these numbers, is equal to this. But that's just the general case when n equals 6. We want to try and prove that this statement is true for all the values that n can take where n is greater than or equal to 1. And the method that we're going to use to prove this is something called a proof by induction. And the way that this proof by induction works is that, first of all, we're going to prove that it's true for the base case. Now the base case is the very first case that we want n to be true for. Here we can see integers n greater than or equal to 1, so our base case is 1. So we're going to show that it's true for base case n equals 1. That's our first step. Then after that, what we're going to do is we're going to assume that our statement is true for some general term n equals k. The reason that we're assuming this is true is because what that allows us to do in the next step is something very cool. Then we're going to prove that it's true for n equals k plus 1 using this assumption. What that means is that if it is true when n takes on a value such as 6 or 1 or 357, then if it is true for that value, if our statement here is true for that value, then it must be true for the value immediately preceding that. If it's true for 2, then it must be true for 3. If it's true for 8, then it must be true for 9. If it's true for 7,564, then it must be true for 7,500 and... that's right, 65. If we can show that our assumption is true, if it is true for any term such as for here n equals 1, we've also got the fact that, like I just showed, if the assumption is true, it logically implies that it's true, the statement is true the next integer. And that's what we're going to prove in this proof. Let's get into it. Our first step, as I stated before, is to show that it's true for the base case, which is n equals 1. So I'm just going to say let n equal to 1, and we're going to show that it's true by showing that both of these sides have exactly the same value when n equals 1. The left hand side, remember, we're starting at the number directly above n, so we'll start at 2, and then we'll add all the numbers up to 1 times 2, which is 2. So this is literally, the left-hand side is going to be exactly equal to 2. Okay, what's our right-hand side? Remember, for this side, we just substitute 1 directly into our expression. So here we have 1 times 3 times 1 plus 1 divided by 2. 3 times 1 is 3, plus 1 is 4. So 1 times 4 on 2, and 4 divided by 2 is simply 2. So here we have the left-hand side and the right-hand side are exactly the same value. This means, say left-hand side equals right-hand side, therefore the statement is true for n equals 1. That's our base case. Now we're going to do the cool logic-y thing. Assume true for n equals k. So the way that we're just going to assume this is true is that we'll just literally put k everywhere we see an n. So we're saying that if the statement's true for n equals k, then if we sub all our k values in, then the left hand side will equal the right hand side. I'm going to leave a bit of space and you'll see why in a minute. Hence, we're going to prove true for n equals k plus 1, when n is that very next integer after n equals k. So when n equals k plus 1, what is this going to mean? That means that everywhere we see an n, which is the number that we're substituting in, we're actually going to replace it with k plus 1. So we'll have k plus 1 plus 1 plus k plus 1 plus 1 plus k plus 1 plus 2 plus dot 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 plus 2 times... Remember, we're still going up in increments of 1. So I'm going to say this is 2 times k plus 2k plus 1 plus 2k plus 2. Because we're still going up in increments of 1, and the reason I can say it's this is because this term here is equal to, I'm just going to write it here, we know that 2k plus 2 is equal to 2 times k plus 1. That's just some pretty simple distribution stuff. So we can just write that instead. This is our left hand side, and this we're going to prove is equal to, for all integers n greater than 1 anyway, is equal to, we're substituting into this n equals k plus 1, so k plus 1 outside times 3 times k plus 1 plus 1 divided by 2. Okay, this might look pretty complicated. I'm just going to start with the left hand side and we're going to simplify that. Left hand side, k plus 1 plus 1 is k plus 2. K plus 1 plus 2 is k plus 3. Plus dot dot dot, going up in increments of 1. 2k plus 2k plus 1, oopsies, let's put a bracket there just for fun, plus 2k plus 2. We might see something interesting that's starting to happen here. All these terms, k plus 2 plus the increments up by 1 up to 2k, are exactly contained here in our left hand side for what we assumed is true. The only problem is that we have this pesky k plus 1. So to get rid of that, and to use our assumption on these terms that we recognize, I'm going to subtract k plus 1 from both sides here, which means I'll have k plus 2 plus k plus 3, because we're going up in increments of 1, plus 2k equals the right hand side, which is k times 3k plus 1 and 2, minus k plus 1. Remember, this is still what we've assumed is true. So if we've assumed this is true, that means that we can replace our left-hand side with what we've assumed is true. If from this assumption, if from what we've assumed is true, we can show that it must be true for the next integer, and that's basically what we've done for our proof. And if it's true for the next integer, it just means that this left-hand side will be equal to this right-hand side. So I'm just going to replace all of what we have here with what we've assumed is equal to up here, which is k times 3k plus 1 on 2 minus k plus 1. And we still have left over these two terms, so I'm going to say plus 2k plus 1 plus 2k plus 2. This is what our left hand side is equal to. And now I'm going to start to simplify that. Okay, so this term is on 2. Our right hand side is also on 2, so I think it's probably going to be helpful to get this all on a common denominator of 2. So we'll have k times 3k plus 1 on 2, And if we want to get these all on a common denominator, what we're essentially going to do is just multiply by 2 on 2, which is actually equal to 1. Multiplying by 1 changes nothing, but that will mean that we can all have a happy common denominator of 2, and they can all go together. So it'll be minus 2 times k plus 1, plus 2 times 2k plus 1, plus 2 times 2k plus 2. And this is all, let me get a ruler, over the common denominator of 2. Okay, this is a lot of letters, but thankfully it's all in k's, so we should be able to simplify it pretty easily. First I'm going to expand this to 3k squared plus k. This becomes minus 2k minus 2. This is plus 4k plus 2. This is plus 4k plus 4. And it's still all divided by 2. Epic. What happens if we collect like terms? There's only 1k squared, so that becomes 3k squared. We have 1 minus 2 plus 4k's, which is 8 minus 2 plus 1, which is 7k's. And our constant terms, minus 2 plus 2 is 0, plus 4 is 4. Divided by 2. Now this is just a simple quadratic person, and we're going to simplify this using our basic factorizing by parts, or something that it's called. So we need to find two numbers that multiply. I was going to say they have a product of 12, and they have a sum of 7. And if you use your Brainium Cranium, you should see that these two numbers are 4 and 3. So we're going to split this into plus 4k plus 3k, because those are our numbers, and then divide by 2. Okay, what do we have? We'll factor out a k out of this. This is 4k outside of 3k plus 4, plus 1 outside of 3k plus 4. Divided by 2. What's this? This is equal to k plus 1 outside of 3k plus 4 divided by 2. And if we have a look, this is very similar to our right-hand side. I'm just going to bring down the right-hand side. This is what our left-hand side is equal to. And our right-hand side is equal to k plus 1 times 3k plus 1. So this is 3k plus 3 plus 1. So that's just 3k plus 4. So we'll have k plus 1, 3k plus 4 divided by 2. What do you know? These two sides are exactly equal. Isn't that crazy? Left-hand side equals right-hand side. We've used the assumption, and we've proved it's true for the next integer if it is true for a single integer. And we know it's true for a single integer, we know it's true for n equals 1, which means it must be true for n equals 2, and then it must be true for n equals 3, because it's true for n equals 2, which means it's true for n equals 4, which means it's going to be true for all positive integers that are greater than or equal to 1. And that's what we had to prove. So I'm going to say, therefore, statement is true for all integer n greater or equal to 1 by mathematical induction, which is the proof that we used.